So up to this point, we've looked at the sampling distribution of the sample mean. Let's take a look at another concept, which is the sampling distribution of a sample proportion. What we have is a situation where in a population, there could be a particular attribute of interest, and in the entire population, the percentage of that population that bears that attribute could be known. Let's say, for example, what is the percentage of red cars in the local population? So if we have 50,000 cars, what is the percentage of cars that are actually red? So I'm just going to draw this. So this could be a proportion of the entire population of red cars. We could probably see that this is 30%. Red cars, 30%. So that population has a proportion of cars that are red, and we'll denote the population proportion by pi, 0.30. And that's just a single value. Unlike, say, the normal distribution for a continuous variable, such as time, in a population there could be several different values of time. But in this case, there's just a single proportion. 30% of the cars are red. Now, if we know that there are, let's say, 50,000 cars, as an example, 50,000 cars, and I were to take a random sample of 100 cars, n is equal to 100, then I would expect to get 30 of them to be red, but it may not be that. So my sample proportion, the proportion of cars, maybe in that sample was 0.28, 28%. If I took another sample of 100, the proportion could be 33%. If I take another sample, it might even go to 35%. Let's call that P3, P2, P1, 0.35. If I take another sample of 100, it could be 24%. So you could see here that taking sample sizes of 100 and then generating the sample proportions, if I compile them all together, P bar 1, P bar 2, P bar 3, P bar M, all the possible values that I could get, we now have a distribution. That is a distribution of the sample mean P bar. And because that's a distribution, that distribution will have a mean, mu P bar, and will have a standard error, sigma P bar. The question is, what are those? And not only that, what's the nature of that distribution? Is that distribution a normal distribution? Maybe it might be. Maybe it may not be. Mu P bar, sigma P bar. All right? So this is what we're trying to do here, is to establish what is the nature of the sampling distribution of the sample proportion, and then demonstrate how we would use that to calculate probabilities. So the sampling distribution of the sample proportion, here we have a population proportion. Now your notes will say P, but I'm going to switch that to pi because sometimes we get P and P bar confused. So I'm actually going to change this later on in your formula sheet to pi. So everywhere you see P, just think pi for now, all right? Because I will change it to pi. And then P bar will be our sample proportion. So population proportion, the fraction of values in a population that have a specific attribute, like the percentage of red cars, percentage of green cars, percentage of adults over the age of 25 that have access post-secondary education. So there's an attribute that we're interested in, or what percentage of the population will vote liberal, or vote NDP, or vote conservative. So that's an attribute. And then we are interested in the proportion in the entire population. But whenever we take a sample and we measure that statistic is an estimate of the population parameter. So P bar, which is a sample statistic, estimates for us pi, the population parameter. So let's keep remembering that. So we want to know something about the sampling distribution of the sample proportion P bar. So just like we did in the case of the mean, sample mean, the sampling error was the sample statistic minus the population parameter. Well, in this case here, our sample statistic, we see it as P bar, but our population parameter would be pi. So if I were to do this with the proper notation that I would like to use, it would be P bar minus pi. All right? And then pi would be the population proportion, P bar would be the sample proportion. So we could determine that sampling error. And then remember that the Z value associated with a sampling distribution is the sampling error divided by the standard error. So we want to know what those are. So examine the nature of the sampling distribution of P bar. So the best estimate of the population proportion will be the sample proportion that we obtain, P bar. Any inference about how close the estimate is to the true population value, that is pi, will be based on the distribution of the sample proportion. So the sampling distribution of P bar, whose underlying distribution is generally a binomial distribution. Now let's just think about the attribute, this idea of the attribute. P bar, or P, is the probability that we have the attribute or not. So for example, if we say 30% of the population of cars are red, so what's the probability that a car is red in the population? It's 30%. Think of the binomial distribution for a change. So either it is red or it is not red. So P would represent the probability of being red. 1 minus P would represent the probability of it being not red. And so that distribution, where you have two possible values, is a binomial distribution. You may recall that from your calculus class or your intro to probability class. And so while the underlying sampling distribution is binomial, we have a special condition under which if the two conditions are satisfied, then the binomial distribution can be approximated by a normal distribution. And this is very important for us because we like the normal distribution. What's the condition? Well, if the expected value of the number of cases with the attribute is 5, and the expected value of the number of cases without the attribute is also greater than 5, then we could use a normal approximation. So notice we take n, the sample size, times a proportion, and we're saying that if that is greater than or equal to 5, and n times 1 minus p, so that's the expected number without the attribute, then we could use a normal approximation. With that normal approximation, we need a mean and a standard error. Well, the mean of all of the sample proportions, mu P bar, will just be equal to pi, the population proportion. However, the standard error is given using this function right here, which is sigma P bar is equal to P into 1 minus P over n. But remember, we're going to use pi. So if I'm going to substitute this, it will be sigma P bar is equal to the square root of pi 1 minus pi over n. Okay? And you can see when the sample size gets larger, the standard error also gets smaller. So that is the mean and the standard error of the sampling distribution. So here we have a theorem which helps us now to make the assumption about the sampling distribution of the sample proportion P bar. Theorem 5 says, regardless of the value of the population proportion, with one obvious exception, P is 0 or P is equal to 1. If P is 0, that means there's none in the population that has that attribute, or if P is equal to 1, then all of them have the attribute. So you don't have varying circumstances. You cannot take different samples and get anything different. All right? So if it's not there, if there are no red cars, no matter what sample size you take, you will not get any red cars. And if all the cars are red, no matter what sample size you take, all the cars will be red. So those two extreme situations, we try to avoid them. But in between, if we have 80% red cars, then we could see different things in the samples that we take. So those are the obvious exceptions. The sampling distribution for the sample proportion, P bar, will be approximately normally distributed with a mean mu p is equal to p or pi, as we will make that change, and sigma p is equal to this expression here, but instead of p we will substitute pi. And of course we need those conditions met. The approximation to the normal distribution improves as the sample size, of course, improves and as p approaches 0.5. If we could get it as close to that as possible, then we'll be doing pretty good. Okay, so if we want to find the z value for a sampling distribution of a sample proportion, we will simply use this formula. Z is equal to the sampling error, which is sample statistics p bar minus the population parameter pi divided by the standard error, which is pi into 1 minus pi over n. Okay? And so that gives us the formula that we require. Now there is something called a finite population correction factor, but we won't use that. We will assume in most cases our population is sufficiently large that we do not consider it a finite population. So this formula right here, which says that if we have a finite population, we would use this adjustment. We could ignore it for the purposes of this course. So how do we use the sampling distribution of the sample proportion to calculate probabilities? Well, one, determine the population proportion, pi, if we know it. Calculate the sample proportion, p bar. Determine the mean and standard deviation of the sample proportion. We already know that mu p bar is equal to pi. And we already know how to get sigma p bar. And then, of course, what is the event of interest? So usually it is the probability that a sample proportion would be greater than some value, less than some value, or between some two values. If both of these conditions are satisfied, right, n into 1 minus p, n times p, in this case would be n times pi and n times 1 minus pi, then we could actually use a standardized z value and use the z function. Use the normal distribution table that would then allow us to calculate the probabilities that we desire. And here's an example for us. I will do another one shortly. But here we have a sample size of 100. X is 73. What that means is in a sample size of 100, we observe 73 cases of our attribute. So which means that our sample proportion is 0.73, which is here. That's our sample proportion. But the population proportion we're given pi is 0.8. Determine the mean and standard deviation. So we know that mu p bar is equal to 0.8, which is the same as pi. And the standard, it says a sigma x bar, but that should be sigma p bar, is just equal to pi into 1 minus pi over the sample size, which is 100, which is 0.04. What's the probability of finding a sample proportion of less than 73% or 0.73? We would simply, if we do the test, we find that NP is equal to 80 and n times 1 minus p is equal to 20. So therefore they both are greater than 5. We could therefore use the normal approximation. And with the normal approximation, here is our z value, negative 1.75. If we look up 1.75 in the z table, the area that we will find, and when you subtract it from 0.5 to get the area in the tail, will give us, this is the probability of p bar being less than or equal to 0.73. All right. So what that means is that the area in the z table that corresponds to negative 1.75 must have been 0.4599. 0.4599, which will give you then 0.0401 when we subtract it from 0.5. Okay? So that's a quick and dirty example. I will do another one for you shortly. So let's take a look at a problem involving sampling distribution of the sample proportion. We have a situation here where the Better Business Bureau of the United States settled 75% of complaints they received. That was in 2009. Let's suppose that you've been hired now by the Better Business Bureau to investigate the complaints that they've received. You plan on selecting a sample of new car dealer complaints to estimate the proportion of complaints the Better Business Bureau is able to settle. Assume the proportion of complaints settled for new car dealers is 75%, the same as the overall proportion in the 2008 census. Suppose we like to take a random sample of 450 complaints involving new car dealers. What is the sampling distribution of the sample proportion? So let's see what data we have. In 2008, we were told that the Better Business Bureau settled 75% of the complaints. So they're settling 75% of their complaints. We take a sample of 450 complaints. So if we take that many, we want to know what's the sampling distribution of the sample proportion. So a sample proportion would just be the number of complaints that would actually be settled in the sample, right? So the sample proportion, if we take 450 complaints, then how many of them will settle? We express that as a proportion. That's fairly easy to do. The sample proportion is usually given by P bar is equal to X, which is the number of positive cases, over N, the sample size. So what is the sampling distribution? Well, remember that the sampling distribution of the sample proportion is a binomial distribution. However, if N times P is greater than 5 and N times 1 minus P is also greater than 5, then we could use a normal approximation. Now I said P here, although I did say that I was going to use pi. So 450 times 0.75, that's 3/4 of 450. We know definitely is greater than 5. And then 450 times 1 minus 0.75, which is basically 0.25, is also greater than 5. So since this condition is satisfied, the sampling distribution of the sample proportion should be approximately normal. So we should be able to say that P bar is approximately normal with mu P bar sigma P bar, where mu P bar, which is the mean of the sample proportions, would be equal to pi, which would be 0.75, because we were told in the question, let us assume the population proportion of complaints settled is 75%. The standard error of the sample proportion we know is given by pi 1 minus pi over n, and then we take the square root of all of that. So pi 1 minus pi. In this case, that would be equal to 0.75 times 1 minus 0.75, or 0.25, over 450. And we would have to take the square root of all of that. What answer does that give us? That's our sigma p. That answer should be equal to 0.0204. So let's make some space for it. So it turns out that that answer is 0.0204, and then we have mu p is equal to 0.75. So now we have those two parts of the sampling distribution of the sample proportion determined. Part B of the question asked, what is the probability that at least 360 of the 450 complaints will be settled this year? So let's just create a little space there for ourselves. All right? We want, what is the probability that 360, right, out of the 450 would be settled? So that means the sample proportion should be greater than or equal to 360 out of 450. So at least that would be settled. What is that equal to? So let's find out what the sample proportion is that we are interested in. So 360, x over n, over 450. We know 9 could go into each of those. 9 into 36, 4. 9 into 45, 5. So that should be 80%. Would be our sample proportion, 0.8. And so we are interested in the probability that p bar is greater than or equal to 0.8. Well, for us to find this, so if our sampling distribution is approximately normal, the mean is 0.75. The standard deviation, remember we computed that was 0.0204, and now we are interested in 0.8 or more. So this is the area that we are trying to compute. So what we do, of course, is we now convert to a standard normal. Z is equal to the sampling error, which we know is p bar minus pi over the standard error of the sample proportion. So that is 0.8, which is our sample proportion, minus the population proportion, which is 0.75. And we've already computed sigma p bar. That's it right here. So we don't need to put divided by the square root of pi into 1 minus pi over n. We already have the value, 0.0204. Let's see what that gives us as a z value. So as a z value, we have 2.45. So the probability that z is greater than 2.45 would be, and that's the area in the tail, so it would be 0.5 minus whatever area is associated with 2.45. And that should be equal to 0.5 minus 0.4929. And that is equal to 0.0071 or 0.71%. And that's the answer to that question. So the probability of getting in a random sample of 450 complaints 80% or more being settled is 0.71%. That's a small proportion. That's not huge at all. So we don't have a situation where it seems like a lot of these complaints would actually be settled. All right? Part question C here, we're told, based on a sample of 450 complaints, what is the probability that the sample proportion would be within 0.04 of the population proportion? So if I were to, I'm just going to block this out here, draw this diagram. So we're looking at part C. So the population proportion is 0.75. We want to know what's the probability that a sample proportion would be within 0.04. So if it's going to be within 0.04, if I add 0.04 to 0.75, that gives me 0.79. And if I subtracted 0.04 from 0.75, that gives me 0.71. Okay? Now, one of the nice things that we know with this particular problem is that because we are looking at 2 points that are equal distance from the center, we only need to find one of them and then double that area to find what we're looking for. Okay? So if you wanted to write this out as a statement, what you're being asked for is what's the probability that a sample proportion p bar is greater than 0.71 but less than 0.79. That's essentially what we're being asked for. Okay? So let us compute. But this, we need to note that the sample size has been changed for this particular question. We changed the sample size to 200. Not 450 as we've been working with, but 200. So our n is 200. So let's find the two z values associated with those 2 points, 0.71 and 0.79. So let's call the first one Z1, 0.71 minus 0.75. Now our standard error will be different because our sample size is no longer 450. So I cannot use the 0.0204. I must now compute that again. 0.75 times 0.25 over 200. It turns out that when I do this computation, the Z value is negative 1.31. Negative 1.31. So negative 1.31, which means that if I were to compute Z2 without doing the calculation, because there's exactly the same distance, the sampling error is the same, so Z2 would be positive 1.31. I hope that you appreciate that. All I would have to do is to go 0.79 minus 0.75 divided by the square root of 0.75 times 0.25 over 200, and we compute that, it will be 1.31. It's the same thing. The distance is the same. So now, last but not least, we just want to make a little more space. I want to just find what is the areas associated with 1.31. So the probability of P bar being between 0.71 and 0.79 is the same as the probability that Z lies between negative 1.31 and positive 1.31. And because the area would be the same on both sides, so this would just simply be twice times whatever the area is associated with 1.31, which is twice multiplied by 0.4049, which gives us 0.8098. So the answer to this question is 80.98%. All right. So the probability of being within 4 percentage points of the population proportion in a random sample of 200 is actually fairly high, 80.98%. And that's what we get there. Okay. So that is an example that shows us how we could work with the sampling distribution of the sampling proportion.